Hello guys, we are going to talk today about advanced lane finding techniques. But before we start, let me introduce myself first. My name is Ahmed Bakr and I am working as teaching assistant in the Faculty of Engineering, and I am also working as a senior embedded software engineer in an automotive company for more than 3 years. Okay, then why are we using advanced lane finding techniques? Why do we need to identify the lanes in any camera images that we took from the car? Okay, it's very obvious. We are trying to build self-driving car, which is trying to move itself in the road autonomously. So we need first to identify the lanes that our car is in currently. Okay, but first of all, we need to calibrate our camera first, because there are many camera vendors in the market, and we have to calibrate the camera to undistort the camera image, because the cameras have multiple focal lenses and something like that. So we will be using chessboard images, actually multiple chessboard images, to calibrate and find an array of the parameters to calibrate our camera. We are using chessboard images because they are very easy to identify the edges of the squares, of the black squares here inside the image, so that it's easy to calibrate them, like these images that I'm showing to you currently, and we will be using them after that to undistort any image. How undistortion process is done? Okay, this is the original camera image that we took from the camera. Okay, and this is the undistorted one. It's obvious now that the undistorted one is very different than the original image that has been taken from the camera. Okay, then the undistorted one is much more better, and we made this process to make sure this works well for most of other camera images like this one. The edges are now very obvious, okay, to be shown. That's very good. And for real camera images from the car, maybe this one, the RGB one, is like the undistorted image. Maybe we can find some other image that's more obvious. This one here, this one is more far, but this one is closer. So the undistorted image is more realistic image that we are using, like you are watching it using your eyes. This is the more realistic one, and this is the unrealistic image that has been taken from the camera. Okay, and in here it is also obvious that this vehicle, all of it is inside the scene, but this vehicle here, part of it is outside of the scene. Okay, this is the undistorted image, so that we can work with it and find our distances with other objects. Okay, then the next step that we are going to do is the top-down view. Why do we need top-down view here? Okay, if you can see it here, when we are inside a lane, okay, then the lane lines are supposed to be parallel. But if you see it here from the RGB image, it's not like there are parallel shapes. Okay, in here these two lines are far away, and in here these two lines are very close. But this is because of your angle of view. But if you were looking from the top, you will be seeing them like they are in parallel. Okay, so that's what we are doing in here. That's the original image, and that's the top-down view, and it is shown here that the two lanes are parallel lines. Okay, that's very, or parallel curve, so that's very good. Okay, and this is another camera image. Wow, very obvious now. This is another one. This is another one. Okay, I think it works now very good. The second thing that we need to do in here is we need to extract some features for the lanes only, because we need to extract only the lanes. We don't need to know everything inside this image. Okay, then now we'll be focusing on finding color channels from the image. So we are using HSV color channels, which are the hue, saturation, and value. We'll be focusing on the S channel and the V channel and the R channel from the RGB components. Okay, And here I'm showing to you the original RGB image, and here is the S channel, the V channel, and the R channels. Okay, and the last one is the SX channel, which is the derivative of the S channel. Okay, very good. If you can take a closer look in the images, you can see that the most better version of the channels is the S channel, because it can accurately identify the lanes inside the image. They are shown in white, and everything in the environment is shown in something like black or gray, so we can use some thresholding techniques so that we can get rid of any black or gray pixel which are not closer to the white one. Okay, so in here the S channel wins, and in this image the S channel also is very good. The V channel okay, but it may see this, or may see this, also may see this as lane because it has the same color, but the S channel is very good, and the SX channel also is very good here in this image. So we have 2 for the S channels and we have 1 for the SX. Okay, and in here this image the H channel is also very good, so that we have now 3 points for the H channel. The V channel and the R channel are good, but the H channel is better, and the SX is very good. And in here the H channel wins again, and the SX channel is very good. Okay, so that we may be trying to use the S channel along with the SX channels. Okay, and in here also the S channel. After all, I choose S channel with SX channels so that I can identify the lanes inside any camera image. Okay, I will show it to you here. That's the output when I combine both the S channel and the SX channels for this original image, and after that I converted this black and white image or binary image into the top-down view. Okay, so that it's obvious that it's very nice, and we can see only the lanes, but there is some noise that we will get rid of very short. Okay, it's very good in here also, and here and in here, but this one is not very good. We will see how we can get rid of these noisy things, and we will focus on these 2 only. Okay, sounds very good. Then our next move is that we need to identify the start position for the lanes. Okay, then we will be trying to find something called histogram. The histogram will tell us where the white pixels are combined in the image, in which column. So in here, in this column, there are too many white pixels, and in this one there are too many white pixels, so that we will be using these peaks as initial position for our lanes. Okay, that sounds very good in here. Also very good in here, which is this one, which is 300, something between 300 and 400, maybe 390, and this one is also very good, which is a little bit closer to 100 and 1200. Okay, that sounds very good. This one in here, this one in here, this one in here, even if this one is noisy, but it can accurately find a good estimation for the start of the lane. Okay, very good. Then our next move is that we will be trying to build or move a window through our image. So we'll be using this window, and we will be trying to reallocate this window so that its center has the most pixels from the lane, so that we will be trying to move this window so that we can get most pixels from this lane. So this one works fine in here, this one works fine in here, and it's very obvious in here, very good technique, but its drawback is that it's slow. Okay, a better thing, we may be trying to find another searching technique for the lanes. If you know before a good estimation for your start position for the lane, you may search using the poly image. In here, we will be using a polyfit to fit a polynomial of the 3rd degree to find the lane lines. So we may add a negative offset and positive offset, and this is only the space that we are searching into. So any next image that we get that's faster than moving a box inside the image to find the lanes. This is a better one. Wow, it can extract the lanes very accurately, and this one also, oh, this one is very bad. We will see how we can get rid of this image using the error handling techniques, and this one is also very good. Wow, that sounds good. And now we will talk about something called ROV, or radius of curvature. Now we have two equations for each curve, this one and this one. And the radius of curvature is that if we are trying to use this curve to draw a very, very big circle, then what is its radius from the center of this circle? That's what's called the radius of curvature. And we are using these values as error handling techniques or error detection techniques, so that we can detect that both lines are in parallel or both lines are far away from each other. We are also using the center of the vehicle from the center of the two lanes, so that it's also an error detection technique, so that we can detect any faulty images like this one. Okay, and the final thing that we are trying to do is that we will be transforming the top-down view or the eagle view into the original RGB image, so that we can identify exactly on the original RGB image where are these lanes. Okay, so that's in here, that's very good or very nice image, and in here we have detected successfully our lane, and here we have detected our lane. Wow, seems very, very nice. And at the end I can show you a video to show you that this technique is very robust and it is very fast. Have a nice watch. And at the end, if you have any questions, you can write it in the comments below, or you can send me a message. We may have another session for answering your question if you have any. And have a nice day. Bye.